That's me.
Okay, so I should be recording now.
I hope it's recording now.
Okay, I don't know if I'm recording my sound, but okay, never mind.
So you can start.
Okay, this is it. Yeah, perfect. So yeah, for the people that doesn't know me, I'm Daniel from the University of Málaga. Lidia and Monica are my supervisors, and we tend to work on software product lines, among other things, but mainly on product lines. My thesis has two large points. The first one is about energy consumption. So we try to reduce the energy consumption of devices. Let's keep it short. And we will use a software product line approach, but with a slight difference to the company. So why, first of all, why energy efficiency? Depending on the country, I will tell a different stuff. But in case of Germany, I would say extreme weather conditions. Probably your summers are getting more warm, and the winters sometimes colder, sometimes warmer, depending on the place. I don't know if you have issues with less water. Also, we have the Russian-Ukraine war because of the fuel resources. So energy is power nowadays, but every year we have less and less and less. So then our aim is to decrease the energy consumption. Here we have a really nice picture of many devices, but just keeping it short, we can say that only data centers, like Google data centers, account for 1% of the total global energy consumption. And that includes airplanes and everything. As you can see, ICT surpassed even the aeronautic industry. That was the one that was in the peak now. Intel published, and other companies as well, with a different numbering, that we can decrease the energy consumption of hardware just by controlling the software, even up to 90%. This will be the best case scenario, obviously. Then we have nowadays those new technologies like the IoT, cyber physical system, smartwatches, smartphones, virtual networks, if you are more into telematics, like my group is. So they are really heterogeneous, whether it's to modeling them or to measure energy consumption. You cannot use the same tools for all of them, or for a large server or a data center, for example. And then the problematics, probably for the ones that are more on my age, you know that before phones, you will charge it for 1 week, 2 weeks, and that will be all. And they were incapable of many things. They were large, but now they're small. Batteries are smaller. They are also really powerful, like computers of 10 years ago. So the demands are higher, but the batteries are scarce. Our objective, each line, it's really important. So as I said, minimize the energy and runtime as well. We don't want to reduce so much the energy that the system is too slow. Also, we want to do it automatically, analyzing the alternative features, usually reusable features. And then based on complete software configurations. Why? I will tell more about this later, but energy consumption is usually measured of the whole system and not of small individual features. This is, I will not stop much here because you all know how I work product lines. Why I say that there is a new approach, instead of building a new product, building code, producing code, what we are doing is giving information to the user of our tools based on SPL. Information that will help the developer to reduce the energy consumption of the software. So it could be graphs, it could be a ranking of features that are affecting, but not producing actually the product. And yeah, we have 3 main points. Those 2, 1 and 2, we will be using those three main pillars in all the talk. But you're more familiar with the variability modeling and the automatic analysis, that would be the solvers. But we add this part, the quality measuring at the configuration level, in this case, energy consumption. This is an example of very simple, I call it like that, very simple variability model. Again, you are really familiar with this. Also because we focus on like heterogeneous devices, as I explained. So this is based on cyber physical system, but this is just an academia model. It's not a real one. As you can see, we have different needs with those heterogeneous systems, different domains of features. We have Boolean features here. We have a numerical feature here. This one is even an enumerated numerical feature, but it could be an unbounded one, like Ethernet integer. We have string features as well. And yeah, we can have complex constraints between them, like Bluetooth and the Ethernet of certain value requires that the vendor has this this naming. Yeah. So then classical numerical features are not enough to represent those heterogeneous systems. We are not even entering into the energy. If we enter into the energy and quality attributes in general, we can see that we have feature-wise quality attributes, but we also have variant-wise quality attributes that are not linked only to single features, but to configurations. So this is, again, a simple example, but if we have compression, Ethernet, and an intervendor, so yeah, it will consume 5 paths. And they also interact between each other. Maybe the cost, there could be one constraint between the cost and the energy. Again, feature-wise quality attributes are not enough accurate for energy consumption because the aggregation formula will be too complex to represent individual values. Again, now I go into quality measuring, specifically energy measuring. We have, it's too complex, as I said, and we have something called quality models. There are some standards. Here is the IEEE, ICO, IEC, blah, blah, blah. So they will have 8 main types and then many subtypes. So energy and time will be under deficiency 1. But the main problem is that they are disconnected from variability model. So this is an independent quality model that's not related with features or configurations. So we need to somehow integrate the variability and quality attributes variant-wise modeling. And also the values of those models here. You cannot see the values, but yeah, values or quality, variant-wise quality attributes. Then the tools are, as I said, those heterogeneous devices are really complex. So here I have an example of a multimeter, but you can guess how many different tools do we need. Also, we cannot automatize the measurement when they are really, really large, because that means doing this for, 10 to the power of 2,000 configurations. Yeah, who will do it? Again, yeah, it's hard. So now regarding the automatic analysis, you are more familiar with this as well. So we have solvers for large spaces, they work. We need also many operations. We have satisfiability, we have counting-based operations, sampling optimization, blah, blah. We also have different solvers. I ordered them by how well they perform for the size of the model. So usually the fastest, for counting specifically, are the sharp sats. Unfortunately, we don't have yet sharp SMTs or those ones, so I summarize in sharp sat. Then we have satisfiability solvers for Boolean plot lines, provisional formulas, you call it. Then we have constraint programming like Claffer for simple arithmetic SPOs. And then SMT solvers like C3 for more complex arithmetics, but it's the one that is the slowest of all of them if you test the scalability. But again, where the variant-wise quality attributes, they are not supported. Yeah. They support feature-wise quality attributes, by the way. We have 3 RQs. Just to go faster, the first one is based on supporting numerical features, so then numerical feature models. The second one is it deals with variant-wise quality attributes. That means colossal models, partially unknown. That means not all the configuration space is measured. And also it can evolve and so on. We can have different metrics, so there are many complexities. And the third RQ is try to unify the numerical feature model solution and the variant-wise quality modeling solution into a single model framework. This is the big picture of all my thesis. In the first RQ, summarize our solution is an optimal numerical reasoning. We will explain this in the next slide. And for that, we produce one tool, Nemo 2. Nemo 1 as well, but the last version is Nemo 2. For the second RQ, regarding variant-wise quality attributes, we developed 2 reasoners. They're actually web apps, so you can access through our website, ADAS and Sabrus, and their outputs as well are different. This is more statistics and graphs, and this is a ranking of features. And then we have RQ3. Yeah, we created, or we defined formally a unified model of variability and quality. I will explain later. Background, again, this is common for all the RQs. Classical feature models, only Boolean features. Numerical feature models, you have arithmetics. extend the feature models, you have feature-wise quality attributes, and yeah, you could have arithmetics and so on. Cost will be an example, and addition will be the aggregation formula of the costs. And other representation of Boolean variability could be propositional formulas or BDDs. Those two are usually the fastest based on the tools for some counting operations, and probably for sampling as well. But still, the quality models and then the variant-wise quality attributes are not supported here. Then models are too large, so we need techniques.
May I ask for, in the last slide, you've shown the difference between numerical and extended feature models, but I didn't quite get the difference.
Numerical feature models, well, if I go back to this one, this would be a numerical feature, also Ethernet type integer, but then those would be the feature-wise quality attributes. So those are linked to features, but numerical features are numerical features itself. So this Ethernet can be present or not and have a value.
But it always costs €9.
Yeah, exactly. But it could be, it could be individually depending on the value. But in this case, it's a single feature. It's not enumerated. So you couldn't, I guess, you couldn't associate an attribute to the different values, just to the feature itself. You can somehow, I know you can somehow model, you use attributes. So you will have some Boolean feature here called Ethernet, and then you will have different values, and then you will have a feature for you, an attribute for each of the enumerated values. But we differentiate them. And also for the RQ3, it's really important because it will be different morphisms, if you know what I mean. It does.
So what I understood is that both are having integer values, but in one model you only allow enumerations, right?
Not only that. If I change the value of Ethernet here, it will be a different configuration. If I change the attribute value, it won't. So the numerical feature modifies the configuration space, but the attributes, I would say not.
Okay, so it's not much about like modeling, about variability bonding, about what I'm supposed to do during configuration, right? What is considered part of the configuration, and what is some additional property that I cannot configure?
Exactly. That will be like, this will be a component of configuration, and an attribute will be behavior of the configuration.
Okay, so can you sorry for interrupting, but can you show again the slide with the two different versions, and what version are you focusing on in your thesis?
You mean here? So I'm in all of them. I'm using actually extended numerical feature models. So I mix all of them. I will support attributes, and I will support as well numerical features, and obviously Boolean features.
Okay, thanks.
So, should I continue or? Yeah.
Yes,
okay.
Please. Thanks.
So yeah, we will use all of these. All I'm presenting here is background for what we use. But again, as I said, variant-wise quality attributes are not considered here in any of those. Then when the space is too large and partially measure all these complexities I explained before, we need some tools to try to get some information of the configuration space. So we have sampling, some statistics, and some machine learning that we can apply. This is a small, just for the ones that are not too familiar with product line and with machine learning. But if I should summarize it in a simple picture, I would say first we do sampling, and then we can do some machine learning regression. That would be if I need a sample that is not measured, for example, for energy consumption, I can try to approximate the value based on neighbors that I have here, or other configurations similar to that one. And then when I already have samples, a set of samples that have some energy consumption value, then I can apply statistics to detect if there are outliers or other kinds of metrics. And also I could use transfer learning based on previous runs of the tool, of the solver, to again differentiate if those features are really affecting or not, because they always appear as high energy consumers. Actually, we can call them here energy eaters, because just to tell that they clearly consume much more energy when they are present on some configuration. Different types of sampling to create subspaces. We have T-wise, random-wise. We have recursive versions of sampling. For example, I use SRS, that is a recursive version of the URS, will be unified random sampling. And we also have probabilistic ones. They will be all used on all RQs. Then for the statistical significance, we have we apply different techniques. One is the chi-squared, and another the Mad-Whitney test, and they are used only on the two first RQs. We also have some approximate regression of quality attribute values that are not measured. So for that, as I said, we will use the neighbors, the KNN neighbors, only on the second tool of the second RQ. And transfer learning will be the same. We use some rank features that we will populate from previous executions, and they will be used only on subrules. So subrules is like the only one that deals with, let's say, machine learning and transfer learning stuff. So solution to the first approach, optimal numerical reasoning. Our solution was bit blasting. Bit blasting already exists. What is new is that we applied to variability models, in this case, numerical variability models, numerical feature models. In really short, what we do is convert numerical features in bits. They are encoded as bits, and the arithmetics will be propositional clauses or Boolean first-order logic clauses. Each numerical feature will be a bit vector, and you can choose different types of encoding. We chose the one most popular on the electronic industry, on circuits, that is a signed integer in a big Indian binary 2's complement encoding. Yeah.
Why? Why do you need signed integers?
Why do we need what?
Yeah, you don't have, so this doesn't represent a number, so you don't need signed integers. Only need
no, but the bit vector represents the value. So if the numerical feature is numerical feature value -3, you need to be able to represent a bit vector that is -3.
Okay. But this isn't a bit blasting, right? So bit blasting would be you have you have a certain set of values for your feature, and then you encode this as as a number.
Yeah, exactly. But it could be a natural one or integer one.
But these numbers wouldn't be negative. It would start with 0, for example, and then would just go up.
Yeah, we have here. I'm showing the integer ones, but we also presented on the works the natural numbers ones. But if you have a numerical feature that can have a numerical, a negative numerical value.
Yeah, of course. If you have an integer feature, yeah.
We are using those ones. But here I just showed yes, the best, the most complicated example. I mean, not most complicated, but the most advanced of all what we did that were the integers.
Okay.
And also this binary 2's encoding allows you to don't represent 0 2 times. So you will not have 0 and 0.
I'm aware of it, yeah.
Okay. Those are the operations that we supported. So most of the arithmetic ones, also you can compose them. If you multiply several times, you will have exponential. But we didn't implement the exponential literally. Here we have two simple examples. If you want to check that two numerical features converted into bits, 1 bit for the sign, 2 bits for values, are equal, you just check that all the bits are the same, and then the proposition formula will be an XOR of each of them. I mean, a distinction will be an XOR. And then for the greater or equal, I should double check now the coding, but first you check that the sign, if one is negative or positive, if it's the first one is positive, you already know that, and the other is negative, you already know that it's greater. If not, you check if it's equal, and then which is the next bit will be the less significant one. And then they are converted to propositional formulas. The less or equal is a conjunction, and then the disjunction keeps on, and equalities are equivalences. This was bit blasting was the application was the first contribution. The second contribution is to define our own numerical variability language in our tool. Our tool is NEMO. I will present it in the next slide. But this is not a true modeling language. It's more like a syntax. But some reviewers complain to call it only syntax. So then we changed to it's published as numerical feature modeling language. This is not the syntax. This is an example of everything you can do, like a cheat sheet of the language. This is how you define a Boolean feature. This is how you define a Boolean feature that already exists in another model. Why? Because NEMO2 allows you to extend feature models. Why we did this? Many old words, what they did is only model the Boolean part of the model. So to save the time to someone to need to model all again with the numerical features, we allow to provide the Boolean model and then only the numerical feature part and numerical constraints, and then NEMO will just join all together. If you don't need to do it like that, you can do it everything from scratch, but we also support that possibility. So that means that this feature B, called here B, it's also feature B in that another model. So it's pointing to that other feature. Here we define an assignment called D between 0, 1, E between 0, 3, another integer, enumerated one, a constant one, and here some constraints. NEMO2 will take care of producing the minimum number of bits necessary to represent the feature, the numerical feature, and also to it will be based on the constraints. If you have a natural and then an integer, then you need to convert the natural to an integer to be able to operate. So we need to increase the bit, but we always try to keep it as to produce the smallest model. We have different outputs here. Here I'm showing just a UVL output. It's not for this one, okay? It would be too large to represent here. But here would be the what we are converting. A numerical feature between -1 and 0, another between -1 and 1, and then C requires that they are different. So this will be the conversion. You can access the last version of the tool here, NEMO2 tool, on GitHub. This is, again, the complete overview, but just focus on this. We have the numerical feature model here, we support it with our syntax, or if you are extending as well, you can provide already a classic feature model and then the extension using the same syntax as here. And then this will all go to NEMO, it will bit blast the model, and it can produce different outputs. You can choose also which one do you want. For now, what we supported is a regular propositional formula in a txt file that usually are compatible with subsolvers. Also UVL, that in our case, we tested on VDD solvers. We know that they are supported on many other ones. But actually, this was tested on Flamma, that also supports what we, for the time, and the best of our knowledge, implements the best VDD solver for classical feature models up to date. And then also the CNF form in DMAX format for, in this case, sharp subsolver. This is a type of sharp subsolver. And then they can be applied to counting, generate products, and sampling and learning, depending on the solver we are using. In short, what we do now is increase the support of regular classical solvers to support numerical feature models. Let's say numerical features or arithmetics. We check the scalability of NEMO2. This is not the scalability of the solvers. This is the scalability of the transformation, the bit blasting part. We tested different synthetic constraints, increasing the number of bits of each of the numerical features. They are all numerical features, by the way. And here you have another set. When you have here 2 or 4, that means we are nesting them. So we will have 4 times this one. We just wanted to check the limits in the number of constraints that we will have and how complex they are for the different operations. Just to keep it short, you can see there are some spikes here. Those spikes are for the most complex operations that usually are multiplication and sometimes division and modulo. Just to give a good number, obviously we can increase the number of bits here, but then we go to the range of minutes. If you keep up to 12 bits per numerical feature, the transformation will be done in seconds. If we go over that, you can see here an example with 16 bits, it already goes to 40 minutes. And it will be worse for multiplication, a little bit worse, etc. No, this is multiplication, I'm sorry. This is all multiplication for different transformation, D-max transformation, propositional formula, and urea. So multiplication is always the worst, then division and modulo. And addition, it's milliseconds. And nesting, it doesn't increment much. This is seconds, not minutes. So yeah.
Can you say what's the general trend there? So is it exponentially growing or quadratically, or?
I don't remember exactly the conclusion, but I'd say that multiplication is none of them are exponential, but multiplication is close to. It's close to.
Okay, what does it mean? It's close to.
I don't think you will see a complete line, vertical line spike, but yeah, it will get close to create that. Actually, we didn't test more than 18 bits because already went to more than an hour. So, but yeah, in short, just keep around 12-bit widths. If you go over that, you can do it. Is it worth it? Probably not, because also the model will be quite large. We evaluated NEMO with different numerical feature models. Probably you are familiar with many of them. The most important is that they have a different variety of numerical features. Remember that this RQ1 was based on numerical features, not on the energy part. And also the size of the computation space grows. This calculation is including the numerical features. And unfortunately, I will tell now in the following slide, but we have this logo here because we couldn't count Munoz. So we couldn't just approximate. Again, those models, they were done in seconds, sometimes even milliseconds. Here it's sampling, so it will be URS, uniform random sampling, and here is only counting with where SharpSat highlights. Also, the BDD sample didn't do too badly. But then SharpSat doesn't have a sampling strategy defined, but the BDD sampler, this is from Ruben Serradio from Munoz, does. So, and also FlamaPy BDD. FlamaPy BDD is really bad compared to, really bad. Less powerful than the BDD sample. All those were compatible for counting and sampling, but VisiBox started to get hard for SharpSat. As you can see, we went to less than seconds to hours. And then for sampling, we couldn't even sample them. So let's say usually Z and G were the desirable limit for us. After that, the models were too large for the current solvers to be counted and sampled. Then we also tested optimization, but here is not the quality attribute, wasn't energy, was something we can measure on the fly. So it could be the size of a compilation, the time of a compilation, of configuration, etc. Those are the number of samples, and also we compared how good is SRS, so the recursive version of the random sampling, compared to random sampling. The numbers are not here, the other table will be too large, but the conclusions were that they work, URS and SRS work equally as good in numerical feature models, bit blasted, to the regular Boolean feature models, but SRS assure an optimal configuration near 0.8, where URS was in the range of 1.4. So SRS was lower, but gave a more near optimal. Then that's over for RQ1. Now RQ2, we get into the variant-wise quality attributes. That means energy. They are linked to complete configuration, not the features. Again, they cannot be modeled on feature feature-wise quality attributes, and by extension, not on extended numerical feature models. This is a representation how they will be linked again, but usually we will have features that regularly live features that conform a configuration, and then they will have a specific energy value, runtime value, or metadata. Here is really the database because it's part of our solution. I will explain on the next slide. And also we have different operations. For the regular feature models, we have satisfiability counting, filtering, constraint, and generating configuration. But you also can have the variant-wise quality attributes version of that. So that means satisfying to know if there is anything that satisfies a certain energy value. So is there any configuration that consumes less than 3 watts? The same for counting and also for filtering. Those are our 2 first contributions of RQ2. First one was to define a database schema that integrates the variant-wise quality attributes and the value, and link by ID, that we assign some ID to the different leaf features. They link, we can say soft link, because we won't have the name of the features or anything in the database. They link a specific variant-wise quality attribute value, for example, 3 watts, 4 watts, 2 different configurations of the configuration space. That doesn't mean that all the configuration space should be measured. So could be that the configuration space is larger and only a few configurations are measured here. This is not only for this works for any energy variant-wise quality attribute, not only for energy consumption. And what we did is a process in the middle. So that will be our second contribution. It was developed on PHP because it's a web app, so it will be the backend. That for the one hand, we have Claffer dealing with the variability and the feature-wise quality attributes. Then we have MariaDB as a database manager for the database schema and information. And then our process will first consult the Claffer. We'll get configurations. Then we'll create a certain set of SQL queries to retrieve the energy consumption values from the database of those configurations in the best and more optimal way. And then we already have the matching of configurations that we create, the configuration space and some energy values that are in the database. Also, why using databases? There are many companies that publish the energy consumption of their, well, not many, but some of them, the energy consumption of their products in databases or datasets. Could be an Excel, but again, similar to a database. So we wanted some solution that is easy, that we can easily integrate those energy values into our solution. This is the overview. You can access the tool here as well. So it will be Hadas CAOSD. The name of it is Hadas. This is the core, what I already explained. So not more to say. Claffer here, MariaDB here. This is the obviously the extended numerical feature model. And then we have some three-folded view interface. So that means that a user, a developer, can click on constraints. So I want this feature to be here. I want that other feature to be there. Then this will be passed to Claffer, and Claffer will consider those constraints and create the configuration space based on the constraints of the user. Everything is done. We already have the metrics, so our process linked all together. And then we can produce, we have different outputs. We have the graphical output, so we will produce different types of graphs. Also, we apply the chi-square statistics, that basically it's to, if we check that one energy value, it's really spare, we will consider it as an outlier. Also, we can have two energy measures for the same configuration. So if they are very different, and one of them is also different for the complete set, we know it's also an outlier. And then this will be provided to the developer, and then the developer is the one just taking decisions based on the graphs. So we are not even giving a specific feature, just showing how different configurations work, perform, and which features those configurations has. We also have like a backdoor to our system. We can call them microservices. That means any other tool can request by a URL all this process. So instead of this, will be done by URL. And in the URL, you will have you can specify features and also numerical features with values that will be the constraints of the model. We also make a plugin that make use of this, a plugin for IntelliJ IDE. And what it does is while you are typing, it will be sending after some minutes some calls to others with converting your code into features. Then Ada detects if those features are in the model. If they are in the model, they will be added as constraints. It will produce all the measure confusion space, give it back to the plugin, and the plugin will present the information as you will see here. Not here, sorry, yeah, as here, as a comment saying these are our suggestions. If those are just configuration, this is how they perform. And then if you want to improve it, the greenest solution would be using, instead of, I don't know which one was used here, but instead of that library, you should use Bouncy Castle for encryption library. You should reduce the algorithm to AIS 128. If you want the less energy consumption, if you want the fastest, then because we also have runtime, we make the same calculation. If you want a trade-off, so a balanced solution, 50-50 between energy and time, then the solution will be different. Yeah. So this is regarding our fourth contribution. This would be the plugin. Yeah.
Isn't the greenest and the balanced one the same? And
it could happen. Yeah.
But it's different measurements at the back. So what's written in parentheses?
Yeah, probably what happened here is that, yeah, well spotted. You can see here some space. Probably it was too large for the slide, so I just cut some of the comment. So there should be more features here. Sorry, there should be more features here. But yeah, also it's not the same measurement. Here you have joules and watts.
Yeah, it's different units. Yeah, just
yeah. But for sure, I also this also happened as well. Yes, shorted. Yeah, I mean, yeah, watts at the end is joules divided by seconds. So it's not watts an hour or anything, it's regular watts.
Yeah.
So it's the rate of the energy. And this was the third contribution regarding the graphical part. So as I said, here you can check, I have these devices, I want to evaluate all of them. Evaluate all, it would be similar to done constraining that subtree. Also, you can define numerical features and a specific value of a numerical feature, also range. And also, you can specify which will be the x-axis, the numerical feature x-axis of the graphs that we will plot. There will be always one numerical feature that will be an x-axis. So for example, here we decide the data length of something we are sending by Bluetooth and Wi-Fi. How does it work for the developer? Yeah, he will see the spikes, he will see that this is configuration, and he will compare by himself, we don't do that, which features are there that are not in the other ones that are behaving better. And also we have something interesting is sometimes there are crosses. So depending on the numerical feature, you can see that at a certain point, it will make all the configurations with that numerical feature higher of that value perform really bad, and sometimes the other one, it will keep linear, so then you know that a specific value and numerical feature also is really affecting the energy consumption of the configuration. Okay, this was the plugin. Then also for the energy measurements, we did our own measurements. This is an example. This is called a WOSMO, small embedded devices. And this tool here is something I got from my first research study on the University of Bristol. It's called the Magic board, and it allows you to perform really accurate energy measurements of really tiny devices. But this board is something between a measuring board and electronic stuff. These would be some results that you get from the readings, and then we convert them to some kind of a table, and then this table will be added to our database. This will be our process. But we only didn't use our measurements of our system. We also got the ones published by the developers of, or researchers of Green Miner, Green Scalar, and Green Oracle. Some example of them are CSVs of the energy measurement of different Java collection classes and different applications. Also, we got some data sets from the University of Bristol regarding different compilation options, how they affect the energy consumption. So, for example, the -1, -01, -02, -03 optimizations. And also some from benchmarks, even from the gaming community, like the Fuentes test suite. We got also some data sets. So they were all included in the our energy measurement database. We also did a small survey of the others tool, more specifically on the plugin. So though there were 17 expert developers, but the experience were different. Some of them more senior, others more juniors. And yeah, just keep in mind, just to go fast, that 3.9 of them recommended, will recommend our tool to other developers. The small value here is just that they didn't think before about something that will help them while coding to reduce the energy consumption. And also the results that we were providing, I mean, the suggestions, they were sometimes they didn't expect that. Usually, that's published, developers doesn't really know, even if they want to reduce the energy consumption, they really don't know how to do it properly. Sometimes they will even do it worse. Then we benchmark the tool itself. So here, now we have a reasoning. Obviously, it's based on Cloudflare, on the database reasoner, and then all the process together. We were increasing the configuration size. That means how many features are in a single configuration, and also the number of configurations. And we can see that everything was done in milliseconds. This is after subtracting the internet time, so the connection, because it's a web app. So we measured this on the server, not on the web browser, because that will depend on the speed of the internet connection. And so then everything was done in milliseconds. And as we can see, the number of features, this column affect more than this column, the number of features per configuration affected more than the total number of configurations. Probably because of the complexity of the subtree that we are analyzing. Those are some results of some evaluations that we did. This was regarding how different web servers perform on different operating systems and so on. This is not the best we have, but it's really easy to spot that some of them behave quite similar for an increasing number of internet petitions or internet requests. Could be websites. So if you are using the worst one here, that was, the best one, because this is energy, yeah. So the best one, the ones that consumes the less, was Nginx. And then you are using the worst one, that is Apache. If you're using this one and you see this graph, you can turn into the gray one. That means you will save around 25% of the energy consumption just by switching which web browser, which web server are you using. But we have we have many tests. Some of them went up even to a 70% of decrease of energy consumption. But again, those are the best case scenarios. But these work for, as I said before, you can see 800 samples, 800 configurations. That's not so much. Someone, and also we need all them. For others, we need to have most of the energy measurements. If we don't have the measurement, it won't be considered. But what if we want completely to measure the configuration space? No one will do it. And also, what happens if it's partially measured? So it's unfeasible to measure everything. It's unfeasible to automatize because the electronic devices, they are really complex. You need some expertise, and also you need to have them close to you. Energy models is similar to the performance models. They are inaccurate if you evolve it, or you reduce, or you add constraints. And also we need some advice in short times. If you are the developer is using a web tool and it's taking 1 hour to produce some suggestion, they will not probably use it. So what can we do? So unfortunately, we couldn't do anything. Not really. What do we do? If you remember, I said that all the machine learning part and transfer learning were used only on Sabrus in RQ2. So here we are. This is the complete approach. This is the most important part. So first, we implement one module. Those are modules that could be changed as well without affecting the other part. We completely made it on different macros. But first, we have the sampling module. In this case, solver-based. Then we have the machine learning part. In this case, we implemented KNN. Then we perform some statistical tests to be sure that the set of samples that we're getting are a proper representation of the space, and also that to check which features are affecting more or less to energy consumption or runtime. Then this sixth step is optional. Transfer learning, that means that if in previous executions of Sabrus, I detected always the same feature as consuming as a high consumer of energy, I will keep a score of it, and then I will be increasing that score. Then here I detect features that are affecting energy consumption in 5, but in 6, I'm ranking them. So the ranking is optional only if we already have previously executions. But they don't affect each other. So the transfer learning will not affect the detection of energy features. Why? Because maybe the system can be, the user can input many constraints that will reduce the system so much that the ranking could be not completely accurate for that subsystem. It's a rework of ADA, so it's also, as you can see, the URL is quite similar, but then we have the Sabrus part. So we rework all the core. For sampling, we implemented 2 options that the user can choose, the recursive version of URS and also the diversified distance-based sampling, DBS. For the regression, the KNN, as explained before, and we decided for the Manhattan distance and dimensions. There are more details in the paper, but it's the one that suits the better for when you are doing a kind of T-wise analysis of features. Then we apply the mine widely U with a 95% confidence to detect that to check that the feature that we are detecting as a highly energy consumers up to 3 Ys. I will explain this. They really are. I mean, we are really sure up to 95% confidence that they are affected. This small asterisk here, that means that first, and this is based on research paper, with the sampling we will check all the 1 Ys, all the features that will be in the samples. If they affect energy consumption, but for 2 Ys, we will only take those that are affecting, that we detected affecting individually, 1 Ys, and then we will check if they also affect 2 Ys. If they affect 2 Ys, that means that the effect will be much greater than the individual addition of the effects. So if feature A increased 1 watt, second, this is not like that, this is a small example. Second feature, we detected that increased also 1 watt. Then the 2 Ys won't be a 2 watts increase. It should be like 5 watts, 6 watts to be an interactive 2 Ys. And then for 3 Ys, we do the same. We check, we will only check triples of tuples detected in 2 Ys as energy consumers. And then the transfer learning is this curve, as I explained, between 0 and 1. So 0.5 would mean we don't know if it's affected or not. 0 would mean it's not affected. It didn't appear before. As you can see, this is 5th contribution. You can see that the input is quite similar to others, but what we produce is again a highlight of features that are affecting and up to 3 Ys asterisk, and a ranking of them. We will not give exact values of how much they consume or how much was the increment. We're just pointing out the one we guess are affecting the most. Then we evaluated them. I have till 2, right? Or half past 2? Yeah.
Including questions.
So half past 2.
No, 2.
2. Okay. So I will try to be faster. The 10 last ones are not interesting because it's more University of Málaga stuff. Okay. Regarding the evaluation, again, different models. This is the only one that is partially measured. As you can see, there is a big difference between the complete space and the partial measurement. And the other ones are completely measured. Why? Because to check the true coverage and true accuracy of our solution, we wanted to have something that is completely measured so we can check exactly how good are the rankings and the features we are detecting. How good are our results? So for this one that is partially measured, as a test case, we were able to reduce this. Again, this is the best case scenario, 90% of the energy consumption based on the worst and the best solution. With only 3% of the samples of the 0 to 25% measurements of the total space. That means 3% of this value here. So we said, the user also can you can see here, can set not only the sampling strategy, but how many samples do you want? Obviously, if you want everything to be faster, you will specify less number of samples. But we checked for those tests 3% of this value samples. So yeah, the results in a test case were good. Now let's go into coverage and accuracy. This can only be done on the ones that are completely measured. So in short, you can see here the times and the coverage and accuracy, but in short, we had a correct ranking 80% of the times with a similar coverage. Didn't change so much between SRS and DDBS, but SRS was more accurate but slower than DDBS. So DDBS was a bit faster. About how testing the limits of the tool with the models, we can see that based on the number of samples that we are analyzing, it tends to get lower, up to, again, it's increasing, but I wouldn't say it's exponential. In short, for a reasonable amount of samples, here are already quite large, 6,000 number of samples. Here we didn't measure it because the model doesn't have too many configurations, so we will need to be using duplicates, and that doesn't make sense. So we have a base time of 1 minute, and then comprehensible number of samples will be in less than 3 minutes, up to 7 minutes we tested for the worst cases. Now RQ3. So we already finished with dealing specifically with varying-wise quality attributes and also the numerical feature that was RQ1. Now we will try to unify everything. Why? Because it's quite hard to do something to maintain one feature model from one side, then all the linking with the database, and also the generation of the queries have some issues. Sometimes could be slow because of different joins, and so we need something that measure all together. And also something that we didn't account yet here is that it's able to specify constraints between feature-wise quality attributes and variant-wise quality attributes. As I said before, the cost implies that the energy should be less than something and the runtime should be less than another value. Then the operations, as I said before, there are some operations that are specifically for quality. There are quality variants or quality, quality-aware versions of it. Like, is satisfiable if one configuration is less than 3 watts? That would be the SAT version, the quality-aware version of the classical SAT operation. We have the interactions, and also we have optimization, so finding the more optimal and some trade-offs. So we need something to model all of them. We will not spend much time here, but before selecting some theory, something that we will choose. Actually, the title of this slide is one reviewer, when we tried to publish this, literally his review was, "Why are you using the exotic category theory?" So we created this table. Just check the reds. It's unsupported, but we need to support it. So this means it's not feasible. It's not feasible. It's not feasible. The yellow ones as well. And this is what a numerical feature model, numerical variability model in this case, will require. And as we can see, category theory supports everything. Literally supports everything because it's defined for that. Then here are some fundamentals. Probably some of you already know that, but what category tries to do is to unify whatever is similar without taking care of what is different, the individual differences of each model. So it tries to unify everything. The main component is the category that is formed by objects and arrows. Defining a category is like defining a meta model. The objects are the main structure of the category, and the arrows are the relationships between the objects. As you can see here, how they are represented as a directed node terms. Then the elements, we have generalized elements that will point to data types, but then we have instances that will be giving a value to that element that we define here to a data type. And those are morphisms. Arrows are also, for the mathematicians, they are called morphisms, but then we have the functors that is different. A functor is also a formula, but the relationship is between category A and category B, between two categories, not between objects that will be the arrows. An example, not in category theory, but you can think of a functor, will be when you are declaring a SQL query. In the select, at the beginning, you are declaring which columns will be in the result. So actually, that SQL query is a functor between the original schema of the database and how do you want to see the results. That will be the output schema. So that could be translated into category A, category B, and the functor between them. Then we get into RQ3, our solution, a quality-aware unified reasoning. Here, the most important is that those two extended numerical feature models were disconnected from quality models. And then what we did is to define a category theory framework where we have different objects. This is the central object that binary link configurations with sets of quality attributes. And then likewise, we have here sets of features. We have features that then will be sets of those ones with form configurations. In this case, only leaf features, and also we have here variant-wise quality attributes here with a value that then, when they are in sets, there will be one quality attribute set. What will be an example of a quality attribute set? Energy 3 watts, runtime 5 seconds. That will be a set of quality attributes. Can be also individual sets, so single sets. This is, I will also not stop much here, but this is a more friendly representation of what I did before. Here you have a model, and you can see that the features here are instantiated here as a complete disconnected, but then they will be connected here on the configuration object. The same for the quality attributes, and also the feature level quality attributes. They are defined as well as a subtype from the feature, so they will be connected to feature directly, not to the whole process of the ID binary relationship. And then here we have the basic domains and the different values for the attributes. But again, keep in mind that everything is about objects and arrows. This is an example of, Paul probably saw this before with me, but when I was here for PhD. But this is a concrete text of modeling a unified numerical quality variability model. And first, we define the main elements. So feature, name, the value of the feature if it's numerical, the domain, if it's string, it's numerical, whatever. Cardinality, that means the cardinality of the feature and the children. And here we'll have the feature-wise quality attributes. So here we gave an example, but each feature-wise quality attribute should be a different element in this category, in this object of the category. Then we have a second object that is the quality model arrows, similar to the feature ones, but name, value, and domain. again, energy 5 watts. And the relationship between all of them, and then here the relationship between all the features that are the complete configuration. Then they are related by a relationship, we call it Phi-C. And then all of these, all those 5 objects are inside the category that we call it here as an example, my variability model category. We use the CQL IDE reasoner for this. They liked it so much, our solution, that they published our research paper and our models in their own website. So if you access the website of the tool, there, as a third-party documentation, will be our research papers and also our models, examples, and so on. We define as well because this is category solver is a really generic solver, so you need to specify, similar to a database, what do you want to perform? Which will be the factor, will be the formula. How do you want that information that is on the category translate to another category? So as an example, one of our algorithms was a report. So this report will calculate from the quality variability model how many Boolean features are, how many numerical features, how many logic constraints, arithmetic constraints, and how many configurations. Keep in mind that we did it in the most optimal way. So if we are doing something that it's only related to the feature model part, not the configuration space, we will only access the feature object. We don't need to go through all the routes. So that's native reasoning, and it's quite efficient. Then here we have for the aggregation formulas. So you specify, for example, the addition for the cost. That will be the algorithm. How it's everything is formalized as and also implemented as a Lambda functional programming formulas, and also for optimization. But again, those are like generic formalizations of the algorithms. This is an example of how the complete framework will be used. So you are a developer and you are using the tool. So first is define, we already did that, we define the category. So it's the schema, again, objects and arrows, and domains of the arrows. We have a parent feature and a child feature. So don't keep it. This is not really complex. This is a really simple example. They are Boolean ones, and then this is an instant of our schema. So this is the meta model, and this will be a model of that meta model. Again, a parent feature and two child features. Then the developer or expert or someone wants to use the tool wants to do a true random sample of that model. We take advantage of the aggregation of operations in category theory. So we will we have something called reusable operations. So sometimes we can decompose. We define the reusable operations and we decompose a more complex operation into more simple operations. Literally, they will be defined like this when you want to execute them on CQL IDE. You will say limit and random. Those are the names that we gave to them. And then, it will produce, similar to a database schema, how we define it, an output. In this case, with two out of the 3 different configurations that we have. Again, this is a model example, it will work like that. Here you can see a real screen capture of the CQL IDE reasoning. Here we define, so they are already defined all the quality aware functions that we would think of. So like satisfiability, considering quality attributes, counting as well. Filtering will be adding constraints of the quality attributes. It could be, again, quality feature-wise and variant-wise quality attributes. Both are supported. And also constraints between them. And also like random sampling and limit will be the, should be somewhere here. No, bound. Bound is will be the sampling, and random if you want to be random. And also we have here aggregation formulas. So sometimes if you want to create a constraint between the aggregation value of the feature-wise to a variant-wise, you first need to aggregate it, and then you are able to create that constraint. Just as an example, this is an example of the filtering, just generating the configurations that matches our feature. And our feature was this one. We want the energy to be less than 18, I think it's watts, and the runtime less or equal than 10 seconds. So it produced 36 out of 63 configurations. We evaluated this with different models, but the most important is that the size were different, the number of measurements were different as well. Actually, this model is taken from the H2020 project that we are working with, so it's based on, it's more like telematics, network systems, and many different types of quality attributes, some of them feature level, and another of them configuration level. And those were our results, using different reasoners for different operations of different kind. Here it's the basic ones, so like the report, number of features, number of constraints, number of quality attributes. Here we have constraining the quality. So that means the cost should be less than 3 euros, energy should be whatever. And here is optimization, so looking for the minimum, maximum, also multi-objective trade-offs, weighted. For example, I want the energy to be reduced further at a cost of energy, but not so large. It would be 0.7 for the energy, 0.3 for the importance for the runtime. And also new domain, meaning that the constraint or the goal is to decrease the watts, but the information in the mode is joules and seconds. So we also support to calculating joules divided by seconds and then doing everything. So that means we new domain. In short, this is our solution running on CQL IDE. We weren't the fast most of the time, but for the feature space solution, Flamma was it's called now Flamma, at that time didn't have that name. It was the fastest most of the time, but we weren't really far from it, so we were quite close. And also you can see this asterisk is that they didn't include in the model variant-wise quality attributes. We did, even if they were not considered here, but that means that the original model is larger. Also, for the bounding, yeah, we were the fastest, but for optimization, we weren't the fastest. Why? Especially in the large models, because we are finding the true optima. We are not doing any kind of prediction. And cite is doing sampling and so on. So yeah, I expected that we will be much faster. So we are not doing here, unfortunately, we didn't have the time to do a near optimal search, but only true optimal. So for that, we analyze the complete sets. So answers, we are able to natively reason and model features, quality attributes, and constraint among them. We define the lambda functions of the different reasoning operations, quality aware reasoning operations, and the evaluation was done in 11 different operations, where our solution was the fastest in most of the time, in some of the times, if not too far, for different 5 different real world sort lines. And this will be more for my true defense. So how many papers did I publish? How many awards did I get? How many research days? And how many research projects I work with or keep working with? But in short, 18 publications only related to the thesis, 3 awards, one of them Best Paper Award, and 3 research days. You can see that you are missing one here, that is the current one. But yeah, I didn't want to add more here, because they will ask me why I did so many research days, because reviewers sometimes. And yeah, research project. The most important is that I'm task leader of one of the tasks on the H2021 demo. And then yeah, those are the publications. Blah 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 blah. So the conclusions you can get numerical features supported. We also define a database for variant-wise quality attributes. Also, we have the SABRUS, so it's the modular approximation and prediction of ranking of features affecting, and also some unified variability and quality framework based on category theory. Future work, integrating other machine learning and transfer learning techniques in SABRUS, or also in the category theory version, that we didn't do that part in SABRUS, yes, not in the category theory. Also change the K and N for A and NN, and also try neural networks or AI, replace relational databases in ADAS by non-relational, test other algebras, test other tools. All knows about this because we've been discussing this in CAOSD, and I still keep in mind to do that when I have the time. And yeah, calculus approximation techniques like Newton approximation represent viability and quality as system of equations. That would be like the integer linear programming area, and migrate and tools to other areas like this with the systems and so on. Yeah, all my thanks to everyone involved in, and that was
There's also applause in the Zoom.
thank you.
Okay, yeah. Questions? We still have 10 minutes.
So you assume that you have a feature model and features are assigned an energy cost? And then you optimize to find
No, energy is assigned to, in all my solutions, this is also debatable, but energy is considered a very wise quality attribute, so they are linked to a set of leaf features that compose a complete valid configuration.
So every leaf feature has assigned a value for energy consumption?
No, one leaf feature, that solution will be a feature-wise, because it's very wise sets of leaf features. That means that one leaf feature can be on different sets at the same time.
So you assign energy costs to configurations?
Exactly.
Okay.
Energy cost, energy rate, if you are talking about watts,
Okay.
and also runtime.
So like I build a variant, then I measure the energy consumption,
Yeah.
then I know it.
Yeah.
And when you want to detect the feature that's causing.
Yeah, I do like reverse engineering. I get the how much the complete configurations are consuming, and I try to see, taking a look at the features, when some feature is present or not,
Okay.
is this really increasing or not? So I'm trying to detect based on complete values. Yeah. But still, I support feature-wise quality attributes, like the regular cost in monetary cost, because the aggregation formula will be simple, like addition or something like that.
So I guess you can do that for any kind of properties, numerical properties related to variance, not just energy.
Yeah, exactly. Yeah.
Do you have an idea what else you could target?
Yeah, I didn't stop there, but in here, as you can see in the third one, you can see that the configuration level one, so the variant-wise one, here we use one that's compilable. So that means if that configuration can be compiled or not. Also, we have here, runtime, and those are, but also for feature level, we also have usability, battery, footprint. We have a mixture of all of them. But yeah, it can be another one that can be a configuration level. At the end, it will be some quality behavior that cannot be expressed accurately with an aggregation function. If the aggregation function is too complex, then it will be automatically a configuration level or variant-wise, and it will be supported by my tools, but by all of them.
Okay.
Yeah. For example, in the first RQ, I didn't talk about energy or variant-wise, but what we did there was to check the size of the compilation of the product, and also how much it took, so that would be runtime again. And there was another one, it was the size, and I think the level of compression was also another one. So yeah. But because the title of the thesis was based on energy consumption, and that was my main focus, everything was prioritized and explained based on energy consumption. Okay. But not necessarily should be only used for.
Daniel, a question related to Sabrina's thesis. So we are looking at feature interactions, and we found that feature interactions that shadow each other are problematic, right? So if you think about sampling, and we have the condition that once you have a feature interaction there, you can also see it. But if there's another feature interaction that is kind of hiding the original feature interaction, we might not be able to see it. Have you experienced something similar with respect to energy consumption? So is it that, I mean, we might have an energy consumption of A and B, but if C is also present, then the energy consumption of A and B is completely different or something like this.
Yeah, for what I understand is that there is some interaction that is so strong, so it will be increasing so much the energy in my case that you will not be able to notice other interactions that at a lower level. Am I right?
Yeah. Yeah, so I'm not quite sure whether this, I mean, you probably have heard of the term error shadowing, right? Which is generally in testing systems, which can happen, but I'm not quite sure whether this is a thing for non-functional properties, whether this can happen there or not.
Yeah, but I get the meaning. We found that we did, but depending of the number of samples. Sometimes the number of samples was too slow, too small, that we weren't able to identify by changing, because we didn't change, maybe that feature was almost always present, so it was always affected. So it can happen even in the other way around. It can happen that because that feature is always affecting and is present in many of the samples, that would mean that our distribution of samples weren't pretty good. We cannot see that it's really affected because it's usually bad. Or there is another one that is also equally as bad as that one, and we didn't get into the sample set one that is not affected. So we have many of those ones, but usually happen when the sampling strategy that we are using weren't as distributed as it should. Also, the number of samples were quite small. But it happened, yeah, in that way that you mentioned, and also in the other way. But it will depend if we have configurations where that feature, that problematic feature, is in and is not in. But it happened, yeah, it happened in energy.
Thanks. I'm sorry, I have to leave now because we're starting for the other meeting in 5 minutes. And I guess you also have to leave, right? Or open the room because the other people probably want to come in.
Yeah, they also have to do something
before 2 p.m. Okay. Yeah, but Dani, thanks for your talk.
Oh, thanks to you.